In this video we will talk about plasma reactors and chemical workbench, its structure, parameters, calculation process and the results obtained. Plasma reactors and chemical workbench are non-equilibrium plasma chemistry reactors including electron-stimulated and vibration relaxation reactions. Plasma reactors are based on numerical solution of the Boltzmann kinetic equation for electron energy distribution function in low-temperature plasma and determination of rate coefficients of electron-induced chemical reactions, energy distribution and electron swarm parameters in gas discharge. Gas composition in the reactors is changed as a result of chemical and electronic kinetics plasma. The time evolution of the electric field in the reactor can be set by hand or determined in self-consistent manner based on the discharge current voltage characteristics and parameters of the external electrical circuit. In general case, the external electrical circuit is simulated by Ohm equation for voltage on an external capacity, inductance of the external circuit, circuit capacitance, and circuit resistance. Voltage on an external capacity is input parameter and can be determined as function of time in table format or user-defined function. V discharge is voltage drop in the discharge and is determined from the current in the circuit using discharge length, surface area, given electron concentration and calculated electron mobility. The rate constant of the processes with the participation of electrons are used to determine the densities of the plasma components and photons from the balance equation that are solved simultaneously with the equations for the electric circuit. In particular cases, one can use the following time dependencies of electric parameters. Reduced electric field is Fermi-like function of time. The function contains three parameters: initial reduced electric field, characteristic time of electric field pulse, and characteristic time of field decay. This function is usually used for short pulse discharges. Current through a discharge is Fermi-like function of time. The function contains five parameters: initial current, characteristic time of current pulse, characteristic time of current decay, discharge length, and surface area. Electric field intensity is determined by current density in plasma. This function is usually used for the modeling of positive column of glow discharges. Zero-dimensional numerical glow discharge model comprised a block of electron kinetics based on solving the electron Boltzmann equation for the symmetric part of the electron energy distribution function. Plasma chemistry model including reactions of neutral species, ion molecular reactions, and the electric circuit equation. The gas chemical composition in an operated discharge differs substantially from the initial one. Therefore, an iteration procedure is required to calculate the steady state. In the course of this iteration, the Boltzmann solver was addressed as soon as electric parameters and gas composition were changed. The Boltzmann equation includes excitation and ionization of atoms and molecules, electron-ion recombination, electron-electron collisions, second-kind collisions, stepwise excitation of atoms and molecules. At the end of iterative calculations, the respective rate coefficients for electron-induced processes were found self-consistently with the gas composition and established current density and electric field coupled through the electric circuit. A system of kinetic equations for charged and neutral species is essentially the system of continuity equations for all species included in the model. The right-hand sides of these equations describe sources and sinks of species including plasma chemical reactions, diffusion losses, and emissions for excited atoms and molecules. As example, let's see modeling of emission properties of the argon-gallium iodide 3 positive column discharge plasma using the Chemical Workbench computational environment. Modeling of argon-gallium iodide 3 positive column discharge plasma will be carried out using non-equilibrium plasma chemistry reactor with electron-stimulated and vibration relaxation reactions, in which The time evolution of chemical composition and gas parameters appears under the effect of chemical reactions, gas-plasma interaction, and radiation at constant pressure and temperature. In this model, current through a discharge is set by hand and is Fermi-like function of time, and electric field intensity is determined in self-consistent manner by current density in plasma. The reactor model is based on numerical solution of the Boltzmann kinetic equation for electron energy distribution function in low-temperature plasma and determination of rate coefficients of electron-induced chemical reactions, energy distribution, and electron swarm parameters in gas discharge. Gas composition in the reactor is changed as a result of chemical and electronic kinetic plasma. The calculation yield the electron energy balance, emission spectrum, and the emission efficiency as function of plasma parameters. The final goal was to predict the emission spectrum and power in the ultraviolet and visible range and the emission efficiency.